Agostino here with Team 14, Shag and Wag, if you will, and my team, Devin, Ryan, Eric, and Corey. And we have partnered with Shagbark Seed Mill, which is a local seeding milling company here in Athens, Ohio, just on Columbus Road. And they produce all nutritious and all organic products, such as corn, various corn products, and dried beans, seeds, and flour into 1 and 2 pound bags, and soon looking to expand to 5 pound bags in the near future. They sell to various places across Ohio, such as local places like Athens Kroger, Casa Nueva, Avalanche Pizza, so many more. And they have a couple clients in West Virginia and Illinois as well, soon looking to expand even further there too. So here is Brandon Jager, the co-owner and manager of operations. And at the beginning of last semester, Brandon came to us and expressed concern for his current system and bagging, which you can see here. Above this system, in the room above here, is a hopper which contains or can contain up to 2,000 pounds of product at one time to be bagged, which will be fed through this PVC pipe here through to a blue rubber nozzle there, which flow is regulated by the operator into bags held underneath, which sit on a scale there. And because of this system, every single bag has to be weighed and measured as it is going. And this could take a lot of time, seeing as the bags have to be measured after every fill. So Brandon expressed that a more semi-automated system where the bags don't need to be measured after every single fill would greatly reduce the time cost for this process. So a couple design specifications that he needed to stay the same were the hopper and the station in the room above, as well as the design for the current bags he's using, need to also stay the same. Maybe some sort of calibration system, so to take into account the different densities of the beans that are being dispensed. So with this in mind, my team and I came up with a couple initial concept designs, and the main differences in these designs are the way that the beans or the product are measured. One of these is through an electronic measurement, which just includes an internal scale, while another one of these is through mechanical measurement, using the use of pistons and cut-off systems. And the other systems you see here are all through the use of volumetric measurement to measure the weight of the beans. And after doing a few decision matrices, we decided that going forward with a volumetric measurement would probably be our best option, and wanted to first test to see if we could use a volumetric measurement to accurately weigh the beans. So while we were visiting the Shagbark Mill one day, we did a simple test of 20 trials, just filling a plastic cup with beans and scraping it to weigh the cup and see if there was much deviation in the different weights of the cups. And after observing the results to see that there was no variation greater than 0.02 of a pound in the cups' weights, we determined that this was a successful test and could move forward with volumetric testing, considering the weight variances in the tolerances of the bags currently produced at Shagbark is the exact same tolerance, 0.02 of a pound. So with that in mind, we came up with an initial design, similar to what you see in front of me. There is the black pipe here, which it simulates the PVC from the hopper above, which feeds product down to the linear slide. The first one here, which will allow the product to fall into the volume-controlled cylinder in the middle of these two linear slides. And this cylinder will be adjusted for size based on the calibration done before the bagging process. The distance between this middle plate and the upper plate will determine the size of that volume-controlled cylinder and can be adjusted with the use of this Acme threaded rod. And then there's one on each side, as you can see here. And once the volume-controlled cylinder is completely filled with the product, the operator will pull back this bottom linear slide until it aligns with a filling funnel, which you can see here in gray. And as the bag to be filled will be held underneath the filling funnel, it will then fall into the bag, and then it can be passed on to be sealed and packaged and later distributed. This entire machine is held together with the frame, as you can see here in brown, which initially we had designed to be made of stainless steel, including this 1/2-inch bottom plate. As I said, there were two Acme threaded rods to adjust for the volume in the middle cylinder. which included linear bearings to hold the middle platform into place. And because we calculated the materials cost for this initial design to be about $2,300, we felt this to have a fairly low value cost ratio. And after some concern with budgets, we decided to take next steps to reduce the cost greatly as much as we could. So our first decision for that was to conduct a Pareto cost analysis and highlight the most expensive parts of our design and see if we could reduce them or change them while still keeping the same functionality of the machine. The main points from this arose the stainless steel that we were using. So in order to work around this, the main platforms, we changed this ABS FDA compliant plastic, as well as the frame. Instead of being all stainless steel, we have changed to an 80/20 extruded aluminum, which will work out a lot nicer with these T-slot slides instead of the linear bearings that were before being used. And we also decided to reduce the amount of Acme threaded rods and bolts to a single instead of two, one on each side. So this will also reduce the costs. Other changes that we decided to make in the design were changes to make manufacturability easier in case something like this were brought to a higher scale. So another point for the ABS plastic is it's much easier to work with. It reduces the amount of welding that would need to be put into the stainless steel. And also bolting together these movable platforms will also reduce the amount of plastic welding that we expected. In this entire machine, we try to use through holes wherever possible to reduce the amount of threading labor that would go into this. And the 80/20 extruded aluminum is so much easier to assemble, especially with the T-slots instead of the linear slides, or the linear bearings, excuse me. And we are now pressure fitting the interlocking cylinders to removable plates instead of into the actual platforms themselves, which will also make installment a lot easier to work with. So as we move forward, we looked at the potential failure modes that we saw in this machine, the most pertinent of which being the jamming of beams during the pushback or pull forward of the operation. So we wanted to conduct a test to make sure that the weight of the hopper in the room above would not create too much resistance when the cylinder is filled. So as you can see in this picture, we created just a simple prototype for these just mock-up cylinders. We filled this cylinder and the bottom cylinder with beams, and then had one person simulate a hopper weight on this top piece, while another person attempted to move the cylinder away from this bottom cylinder. And after seeing that was little to no resistance in this, and resulted in no jamming of the beams, we felt this was a successful test, and that we could continue forward with this same design. And our next failure mode, which was an analysis on the frame of our design. Now, using the 80/20 aluminum, we were worried if there would be an unexpected load causing any sort of deflection in the beams from too much stress. So quick finite element analysis showed us that at the most critical point of this frame, we expect little to no deflection based on the high factor safety and the rigidity of the 80/20 aluminum that we're going to be using. So we also felt this was a successful test, and we decided to move to the last failure mode that we expect, which could arise from the single Acme threaded rod that we're now using. And if there is improper adjustment in this rod, we are worried that there could be a malfunction of the part, or maybe simply just an inaccuracy of the filling of the bag. So as our prototype comes to a completion in assembly, we can finally test for this. And if we do need to redesign, then we can redesign the Acme threaded rods for precision in height or and ease in adjustment to work around this. So with these failure modes being analyzed and the design changes that we made, we now come to a final design which reflects more closely what you can see in front of me. And the materials cost for this are reduced down to just under $1,500, which is a very satisfying reduction compared to the price that we had before. So my team and I view this to be a very high value to cost ratio, especially compared to our initial design, and are moving forward with this currently. And we move to safety concerns, which the main being pinch points during operation, basically when the operator's hand is moving forward and backward on this linear slide. If there's a potential for their fingers to get caught in these sides of the slides, that was a main concern, so we'll have to do tests for that, and to make note of that during a user's manual or instruction guide, as well as a safety guide, and probably require for employees to be trained on this machine before actually using it on site. Another safety concern arises with the ergonomics of this, and not only is there a simple, easy to grip handle to use, but another main point that Brandon noted to us was that employees can be using this for hours at a time, and that could really take a toll on your body if they're having to stand for the entire 2 to 3 hours that they're working on this. So the fact that an employee can sit down and operate this for the entire shift that they're working on it will greatly reduce the strain on their body. So then we can look forward to our expected schedule, and we are proud to say that we are very ahead of schedule for the prototype completion date of March 18th. As you can see here, our beginning and expected ending dates are much later than our actual completion dates are arising. So we're happy to say that this will hopefully create a lot of leeway in our project as it moves forward, and if we run into any sort of complications or problems down the road, hopefully we'll have a lot more time to address them and work around them. And moving forward, as our prototype assembly eventually comes to an end soon, we can finally test for that last failure mode and soon create a safety guide and user's manual. And our team is confident in the approaches that we've used in the design tactics, and working with our partner and our mentors, we look to have the same quality and attention to detail that we've had thus far. Thank you.